part C.2, verify Fibonacci formula special cases. So we will use two steps. The first step, special cases, then general cases. All right. First, our goal, we want to show that this formula is correct. Okay, yeah. It is not that easy, yeah. But because we can see the formula, right? So basically, we just verify it. Yeah. So that will be a little easier than finding the formula. Finding the formula is much harder than verifying the formula. Yeah. All right. To verify the formula, here we need to use a powerful tool that we used before, mathematical induction. Yeah. So we use it in that problem, binary bits problem. Yeah. So here, let us use this one another time. Yeah. When we use it, we need to first check base cases, right? Sometimes one single base case, sometimes probably we need more than one, right? More than one. Yeah. Here, although if we verify two base cases, it's enough. Yeah. Why two base cases? Because based on the recurrence relation, how many terms at the right-hand side? Two terms. Two terms, that means we only need to verify the first two base cases. Yeah. But here, in this video, I like to verify a little more special cases as practice. Yeah. When we do the verification, I want to show you some interesting techniques, tricks to do the math calculation. Yeah. All right, so let us start with special case verification. Yeah. The first one, F0, so if we just plug in n equals 0 in the formula, very easy to see it is correct, right? Yeah, because 0th power, that's 1. 1 minus 1, that's 0. Yeah, so F0 equals 0. It is trivial. Yeah. Excuse me. All right, F1, now let us calculate F1. Yeah, but this time, excuse me. Yeah, we need to do a little more work, especially the second term. Yeah. The second term, we like to convert it to another more friendly form. Yeah. Root 5 minus 1 over 2. Yeah. How can you get that? Here, let me do some quick explanation of that one. Yeah. Here, we just do, a standard way for simplification. We call the rationalize the denominator. Yeah. So what do we do? We multiply root 5 minus 1 over root 5 minus 1. Right? Yeah. So when we do this kind of operation, so you will see this is root 5. Yeah. Yeah. We use the formula a plus b times a minus b equals a squared minus b squared. Yeah. But because we can switch root 5 and 1, the order, so root 5 becomes a, b becomes 1. So a squared minus b, a squared, that's 5. 5 minus 1, 2 times root 5 minus 1. Yeah. So this equals 4, do cancellation, 2 and 4 cancellation, we get this expression. Now, if you use that expression, you can see same denominator 2, then the numerator minus 1, 1 cancel out. Root 5, you have 2 root 5. 2 coefficient, you can cancel with the denominator. So finally you have root 5 over this root 5. So you get answer 1. Now, here you can see you need to do quite some math work. Yeah. But we will verify f1 equals 1. Yeah. All right. So for the mathematical induction, f0, f1 verification already enough. But here, in order to show you some mathematical tricks, I like to verify 2 more Fibonacci numbers. Yeah. F2, yeah, let us look at F2 here. Yeah. F2, we need to calculate this expression. Yeah. So let us plug in. Yeah. After we plug in, yeah. Remember, the second term, we replace it by our previous calculation. We have it. Yeah. Root 5 minus 1 over 2, parenthesis squared. Yeah. Then we use the sum of square of sum formula, right? Square of sum. Yeah. So do you still remember a plus b squared, that formula, and a minus b squared, that formula? Those 2 formulas. So we get the first square representing this fraction, second one, that fraction. Same denominator 4, the numerator, 2 numerators adding together, cancellation, 1 cancel out, right? 5 cancel out because minus, right? 2 root 5 minus negative 2 root 5, so positive 4 root 5. 4 cancellation, root 5 left. Root 5 and the leading part, coefficient part, root 5, cancellation, denominator. So you will get F2 also 1. Yeah, so F2 equals 1. So we verify another special case. All right. Then, for this video, the last special case. Here you can see the verification becomes harder and harder. Yeah. For F3, this time, we need to calculate phi cube and 1 over phi cube. You can imagine how much work we need to do here. Is it too hard? Yeah, we will see. We have to use some special technique. Yeah. Otherwise, probably too hard. For most of you, probably it's too hard, right? Yeah. But we try to find a smart way to calculate it. Yeah. All right. Here, let us do the calculation. Yeah. First, we want to find some effective strategy here. Yeah. What strategy do we use to make the calculation as simple as possible? Yeah. Yeah. The strategy we are going to use here, yeah. First, we need to find why it is so hard to calculate. Yeah. The main reason it is so hard to calculate because the degree of the term, main term, phi cube, relatively high. Degree too high. So when we do the multiplication, it becomes harder and harder. Yeah. So to make that calculation easier, let us take this strategy. Yeah. Directly work on the degree part. Yeah. Reduce the degree to make the calculation easier. Yeah. That's the strategy, all right? Reduce the degree. The lower the degree, the easier the calculation. How about that? Okay, yeah. So that's the simple fact we like to use. Yeah. But the question is how to reduce the degree of phi cubed. How do you reduce it? Right? Yeah. Because here phi is the golden ratio. It is a special number, golden ratio. So we can apply some special properties of the golden ratio to do the degree reduction. Yeah. What kind of special properties? Yeah. So let us from the root part. Yeah. All right. To calculate phi cubed, we can write it as phi times phi squared. Split the term into product of two expressions, phi and phi squared. All right. Why it is better to split it in this way? Yeah. So because in this way, we can apply some special property of the golden ratio. Yeah. So let us look at the property. Yeah. First, we know how do we get that phi number, right? How do we get it? It is a root of x squared minus x minus 1 quadratic equation equals 0. That quadratic equation. Yeah. That means if we plug in phi into this equation, we get phi squared minus phi minus 1 equals 0. We have this identity or equality, right? This equality must be true. Yeah. All right. From this identity or equality, we can write two formulas, two identical expressions. Yeah. The first one, phi squared equals phi plus 1. Yeah. Because we just move these two terms with a negative coefficient, move to the right-hand side of the equality, we get a plus sign, right? So phi squared equals phi plus 1. That is the first property. The second property, we can write 1 equals phi squared minus phi, right? We just move negative 1 to the right-hand side. Then switch two sides. 1 equals phi squared minus phi. That's the second property. So we just use these two properties. We can handle a lot of expressions related to the golden ratio. Now, here, let me use these two properties for F3. Yeah. So now we are ready to do the degree reduction. Yeah. The first term, phi cubed. Yeah. Now, from here, look at this phi squared. Do we have phi squared? Yes, we have it. Our first property, phi squared equals phi plus 1. So we can replace phi squared by parenthesis phi plus 1. Excuse me. All right, next. Multiply through equals phi squared plus phi. Can we replace this phi squared by another phi plus 1? So we will get 2 phi plus 1. How about that? You can see with this new expression, 2 phi plus 1, we reduce the degree from 3 to 1. Original highest term degree 3. Now the current highest term degree, that's 1, right? Yeah, much simpler, right? Degree 1. Yeah. Next, 1 over phi cube. Yeah. So this time it is a little harder because phi cube is at the denominator. Yeah. But we can do the degree reduction, but in a special way. So what is the special way? Yeah. Here, look at the denominator. It's 1, right? Do you notice 1 appears in our second property? So can we replace 1 by phi squared minus phi? Yeah. So this step, you need to really feel comfortable with this step, because usually people feel 1 is so simple. Why you replace a simple 1 by a more complicated expression, phi squared minus phi, right? Usually people don't like to do that. But here, we should do that. Even if we replace a simpler expression by some more complex expression, there is some advantage of this way. Yeah. What is the advantage? Because after this substitution, you will see the numerator and the denominator, they have common factor. You can do cancellation on the common factor phi. That will, after the cancellation, you will reduce the degree of the denominator. We like to reduce the degree of the denominator, right? Yeah. All right, so let us do the cancellation. Now the numerator becomes phi minus 1, denominator phi squared. All right. Then the next step, can you see another one? Here, it's 1. 1 is special, right? Because we can apply the second property another time. Replace 1 by parenthesis phi squared minus phi. All right. So now let us do another substitution for 1 term. Now, after simplification, we will get 2 phi minus phi squared for the numerator. Yeah. Then you will see common factor between the numerator and the denominator, phi, so we can do another cancellation, right? Yeah. After the cancellation, we will have 2 over phi minus 1. Now, I think we are ready. Yeah. So we are ready. Yeah. Although you may like to do another substitution, right? Yeah, you can do another substitution. Yeah, but here, because here we can do the calculation. Yeah, so let's do it. Yeah, phi cube plus 1 over phi cube equals, because plus 1 minus 1 cancel out. Yeah, 2 coefficient 2 and the numerator, we can factor the 2 factor out, so we will get phi plus 1 over phi. This corresponds to F1. That corresponds to F3. Although we need to multiply 1 over root 5 both sides, right? Yeah. So we will get F3 equals 2F1. But 2F1 we know equals 1. So that equals 2. So we verified F3 equals 2. Yeah. But here, some of you may like to try our old technique another time. Yeah, here, let me just quickly use 1 minute to do it. Yeah. 2 over phi, can we write 2 as 2 times phi squared minus phi, right? Over phi. How about that? Yeah. Then we will have 2 phi minus yeah. All right. Right. 2 phi minus 2, right? Yeah. 2 phi minus 2. Yeah. Yeah. All right. Yeah. So then, yeah, here you can see if we do this way, combined with the phi cube, it may not be easier, right? It may not be easier. Yeah. So look at that. It may not be easier. Yeah. So it looks like it's better we do not do another substitution, right? We do not do another substitution. We just use this expression. We can do faster. Now, sometimes we need to control where do we stop. Here, we need to stop at some right place. Yeah. All right. Now, you can see we verified 4 special cases. F0, F1, F2, and F3. Yeah. All right. So we complete video C.2. Our next video, now we are ready to prove the general case by mathematical induction. Yeah. All right, so let us stop here. Yeah.